Thank you. First of all, I'd like to thank the organizers for putting together this nice workshop and for giving me the opportunity to speak. And so today, I want to discuss some techniques which are quite useful in order to study excitations in models of topological phases. And I will illustrate these techniques with a special class of models that have a higher gauge theory interpretation, whose input data is like a categorification of the notional group, namely a strict group. And this is work with in collaboration with Alex Bolivant, who's the next speaker, actually. So during this talk, by a topological phase of matter, I will mean the following. An equivalence class of gapped local quantum models that have a common low energy description in terms of the topological quantum field theory, TQFT. And my focus will not be on these TQFTs per se, but really the quantum models that are concrete realization of a given phase. And more specifically, I will consider models that you can build in a rather canonical way from a state-sum TQFT. And in that case, I will refer to them as the lattice Hamiltonian realization of the underlying TQFT. So for instance, in 2+1 dimension, models of non-chiral topological phases can be constructed from the so-called derive state-sum TQFT in its fully extended form. The input data being a so-called spherical fusion category, and this construction, the lattice Hamiltonian realization in that case is referred to as a stringlet model, and it's due to a Levinian one. So let me sketch a bit loosely the the relation between the lattice Hamiltonian and the underlying state-sum TQFT. So let's say I have a D+1 dimensional state-sum TQFT, a topological lattice model consists of an oriented D-manifold surface, which I equip with a discretization, usually with a bit of additional structure. So for instance, triangulation, or I will later consider cubulation. Then we need a set of classical configuration variables, which we assign to the cells of our discretization. And the microscopic Hilbert space of the theory is then given as the sort of formal linear superposition of these colored cells. The Hamiltonian operator generically is obtained as a sum of local operators, which act on local neighborhoods of the cells of my discretization. And these local operators can be neatly defined in terms of what the state-sum TQFT assigns to a special family of cobordisms. And then this is kind of the key point, because then we can use the topological invariance of the theory to infer a lot of properties. So for instance, the topological invariance will imply that the operators are projectors and they are mutually commuting, such that the model is exactly solvable. And the ground state subspace of the Hamiltonian, which is by definition the space of states that satisfy the stabilizer constraints. So this H phi equals phi condition. So for every operator, there is one such stabilizer constraint, and the states satisfying all of these are ground states. And then this ground state subspace turns out to correspond to the vector space that the TQFT assigns to this space.
Furthermore, I have a very naive question. So you, of course, I don't know at all what's going on, but how is it you want this phi in the definition of the ground state to be an eigenvector of H with eigenvalue 1, and not 0, right? Usually, because oftentimes.
Yeah, I mean, you can rescale your Hamiltonian such that it would be 0, but written as it is, in that case, the ground state will be.
Yeah, just usually, right? If you normalize the ground state energy,
sure,
say that it's 0.
You can write 1 minus the operators instead of the way I've written it in that case. Yeah. And furthermore, it follows from the topological invariance that if I pick a different triangulation or different discretization, the ground states subspaces are isomorphic. And this will turn out to be quite useful in practice when we do computations. So I already mentioned in 2+1D the string net models, right? So the dictionary in that case, more specifically between the TQFT and the Hamiltonian picture, is the following. We have that the ground state degeneracy, which is the number of independent states in my ground state subspace, is equal to the number that the TQFT assigns to the manifold sigma across S1. Similarly, as already mentioned, the ground state subspace is what the TQFT assigns to the corresponding space. And excitations, finally, which is really the feature I will be focusing on. Excitations, which are by definition microscopic states that violate some stabilizer conditions, right? So they don't fulfill all of them. And these are found to form, or they correspond to the objects in a rather famous category theoretical structure referred to as the Junfeld center of the input category. This will not be crucial for my talk, so don't worry if you don't know these notions. And these...
sorry, Clement, one more technical question. So people are asking whether you can share with us your slides. If it's complicated, then forget it. Or if it's easy, you can simply paste the PDF file in the chat. And then people can, whatever, maybe they want to return and check some things that you were talking about some minutes ago. That's usually very convenient.
Yeah.
Thanks a lot.
Okay.
Now there it is. Thank you.
Okay, and so the reason why these excitations are interesting, right, in these models is because in 2+1D, they correspond to quasi-particles with an Anyonic statistics. So mathematically, this is a statement that these provide representation of the braid group. Physically, this is a statement that these particles have statistics that is beyond the bosonic and the fermionic one. And in order to appreciate the fact that we can have anyons in 2+1D, there is this famous cartoon, which is that if you have two particles, right, you can exchange them following a specific trajectory. And then the double exchange of these particles, so it's like going back to the original position, is equivalent to fixing one and going around with the other one. And then the loop described by this particle in 2+1D can be topologically non-trivial in the sense that it cannot be contracted to a point because there is the other particle obstructing. And therefore, the corresponding process is not necessarily the identity, which means that these phase factors exponential I-phi are not necessarily plus or minus 1, which would give us bosons or fermions. And the same picture also allows us to understand why we cannot have anyons in 3+1D. Because if you have an extra dimension, you can use this dimension to contract this loop to a point, and therefore the process has to be trivial. But using similar arguments, we can intuit that if we had higher dimensional particles, so let's say string-like or loop-like particles, then these could actually have maybe an Anyonic statistics. So let me focus now on a special class of models, which is like, so it's a special case.
If it's a higher dimensional, what will happen? I just missed that.
Well, the point is to say that, okay, we know that point-like particles will have to be bosons or fermions. But if we have higher dimensional particles, well, quasi-particles, so let's say like it would be like a string-like excitation, a loop-like excitation, these could, in principle, have statistics that is beyond the bosonic and fermionic one. So in order to compensate for the fact that we are in higher dimension, we need to have higher dimensional excitations.
Thanks.
Does it make sense?
Maybe later. Thanks.
I will describe later what is the statistics of this loop-like excitation, explain in which way they are anyons. So, so a special case of or special class of stringlet models are given by picking the input category to be this category of G-graded vector spaces. And what matters right now is that this has two, the input data of this category is a finite group, G, and a cohomology class in the third cohomology of the group that characterize the monoidal associator of the category. And these models, they're nice because they have a gauge theory interpretation. So how are they constructed, roughly? The microscopic Hilbert space is given as the formal linear superpositions of group-colored triangulations, where by that I mean we put a group variable on every edge of the triangulation, and this defines the notion of G of group connection. So it's like the space of group connection. Sure. Then the Hamiltonian operator is given as a sum of two families of operators, so A and B, that are labeled by vertices and plaquettes of my triangulation. And these encode the two kinds of constraints. So the first one is a gauge invariance, because I said it had a gauge theory interpretation. It's a gauge invariance that is sort of twisted by a phase factor that depends on the input 3 cycle. And there is another constraint, which is a flatness constraint, which essentially penalizes a non-flat G connection. So, okay, and now, since it's a special case of what I mentioned before, we know that the excitations, they will be characterized by this center of the input category. But what's really nice about this model is that there is an equivalent description of this category in terms of modules or representations of the so-called quantum double of the group, which is an algebra. And the reason this is nice is because this algebra shows up quite naturally in the Hamiltonian picture in different ways, but in particular as the so-called algebra of excited states. And I will explain now what I mean by that. So in order to reveal, what we want to do now is essentially to reveal this algebraic structure, because then we know that just taking the representations over it will give us...
I'm sorry, I missed again. So the point light is in the bulk, or?
Yeah, the excitations are, I just wanted to emphasize that these are bulk excitations. So there is no boundary at this point, there is no gap boundary. It's really a bulk excitation.
Okay.
So in order to reveal this algebraic structure, we're going to use the so-called tube algebra approach. So in general, if I think of an excitation as a region of my manifold for which the energy is higher than the one of the ground state, the tube algebra approach relies on the following idea, which can be motivated in different ways physically, namely that the properties of an excitation are encoded into the boundary conditions of the manifold obtained by removing this region. So let me make this more precise. Let's say we have a point-like excitation. There will be a region around this point-like excitation, a disk-like region for which the energy will be higher than the one on the ground state. Now, if I remove this region, I'm left with a circle boundary, right? Boundary that has a topology of a circle. And my Hamiltonian or my ground state projector does not act on this boundary that I just created, which means I have now boundary conditions. And the idea is that classifying these boundary conditions is the same as classifying the point-like particles. So I have some drawings below. So the red region is my region with a higher energy, right, which I removed, and I have this circle boundary. And now, purely at the topological level, I can do the following, which is to glue a cylinder on top of my circle. And then I can use an orientation-preserving diffeomorphism in order to absorb this cylinder on my surface, so that I'm back with the original surface. So in other words, it's like gluing a cylinder on top of my boundary does not change the topology. Now this induces a map at the level of the ground states. So now the idea is that, I want to translate algebraically this topological statement. And to do so, I'm going to lift it at the level of states, ground states on the corresponding manifolds. So what I mean by this is that this induces kind of a symmetrical operation where I'm acting with ground states on the cylinder with ground states on my open manifold, and I will be the result will be again a ground states on my open manifold. So let me make this a bit more precise. So similarly, right, we can do the similar topological operation. We can take two cylinders, glue them, right? So we're just left with a bigger cylinder. And then with the diffeomorphism, we can just sort of reduce its length so that it looks like the original one. Now, again, at the level of the ground state subspaces, right? This induces, in that case, an algebra structure because I'm starting from two states from the two copies of the ground state subspace of the cylinder, and the result will be a state in the original ground state subspace. So how is it defined, this algebraic structure?
Clement, just an clarification. Why are you saying that this algebra is semi-simple?
Well, you can show it semi-simple. I mean, from what I'm explaining right now, it's not, of course, obvious, but you can, once you have it, you can check that this is associative, semi-simple, and you also have a star algebraic structure.
Okay.
Yeah. So how is it defined, right? So you take two states, right, in the two copies of the ground state subspace. Then, so the gluing operation, algebraically, how it translates, well, it's an identification of the boundary conditions. So we have boundary conditions on these circles, right? And the circles along which we do the gluing, where we have to make sure that the boundary conditions match. So in practice, it means that we're going to multiply by some Kronecker delta that enforces this matching. Now, the subtlety is that the resulting states are not necessarily ground states anymore. Which means we need to act with the ground state projector in order to recover our ground states. And once we have this, we can do a unitary transformation, which is the algebraic translation of the diffeomorphism. And at which point we have a state that is in the original vector spaces, and that's how we have an algebra. And this is what is referred to as the tube algebra. And the notation here is so it's the tube algebra associated with the circle.
Can I ask a question?
Uh-huh.
So why is it when it's glued together? Why do you say that it is not the ground state anymore, or it might not be the ground state?
So the ground state projector does not act at the boundary, right? So if I look at the cylinder, right, on the edges, right, or on the boundary, the ground state projector does not act. Then this operation here is just identifying the boundary conditions. So there is no reason why, for instance, the gauge invariance is, in the case of gauge models, should be enforced at the meeting vertex, the vertex at which they meet. Because this is a vertex that was previously on the boundary, now it's in the bulk, but there is no reason why the gauge invariance should be enforced there. So we have like a new bulk vertex, and we have to ensure that the gauge invariance is satisfied at this bulk vertex.
All right, I have another question. So the cylinder you drawed, each one does not have the structure of cylinder alone. It also has some boundary conditions on it, right?
Yeah, so here, okay, it's a bit of a symbolic notation, right? What I mean by my notation here is that the V, right, is the ground state subspace for the cylinder. So then in practice, I will have to actually write down such state. I will pick a triangulation, put labelings on the edges, and this will define like explicit states.
But most importantly, it also may have some different boundary conditions on it, right?
Exactly, yes. So, I mean, the here boundary conditions, what it means that if you want the group variable or the holonomy along the circles along which the gluing is performed is not necessarily the same. So we have to make sure this is the same when we do the gluing.
Okay, I get it. Thank you.
Okay, so putting everything together we have so far, this induces that the ground state subspace on the open manifold has a module structure over the tube algebra. And what we need are essentially to find the simple modules, and this will classify the boundary conditions on my circle boundary. Now, again, to do this, in practice, this is not exactly what we do. We use the following trick, which is that, so starting from my original surface, before gluing the cylinder, I could use a diffeomorphism in order to make my the region around the circle look like a cylinder itself. And at the level of the ground state subspaces, it just means doing a local unitary transformation. Then when I glue my cylinder, the effect of this is that it allows me to localize the action of the cylinder states on degrees of freedom that are contained within this cylinder shape itself. And then I do the same diffeomorphism to go back to the original. And then the consequence of this is that the boundary conditions, they are actually classified by the simple modules over the so-called regular module of the tube, which means essentially treating the tube itself as a tube module. And at the end of the day, the computation we're going to do is to find the irreducible representations of this tube, and this will classify the point-like excitation. Now, as I mentioned before, briefly before, to answer the question, in order to make this explicit, right, we're going to have to pick a triangulation of the different manifolds, define the group connections on it. I mean, define explicitly these ground state subspaces. And then you can ask, okay, but if I choose different triangulations, maybe it will change the tube algebra, maybe it will change what I'm classifying with. And what saves us is that for the cylinder, if we pick a different break triangulation, we can show that it will yield an isomorphic algebra, and therefore it's fine. And if we pick a different boundary triangulation, then it's a bit more subtle, but we can show that the tube algebras are in that case Morita equivalent. And we know that Morita equivalent algebras have the same simple modules. And therefore we know that whichever triangulation we choose, we will always classify the same simple modules. Okay, so once we have a tube algebra, in general, these tube algebras, the irreducible representations, they can be labeled by two elements. An orbit, which is, it's an equivalence class of boundary coloring that are related by the action of my tube, and a representation which decomposes the action of the tube that leaves the boundary coloring invariant. So let me make this right away more explicit in the case of 2+1D gauge models. In that case, the ground state subspaces on the cylinder, it's quite easy because it's the same as picking a flat G connection. And to define a flat G connection on the cylinder, we only need two group variables that correspond to the holonomies along and around the cylinder. And when you apply the tube algebra approach to this, then you find that the tube algebra is isomorphic to the quantum double, which is the algebra I mentioned earlier. The irreducible representation of this quantum double are well known. There are two components, right? So the orbit, in that case, is the conjugacy class of the group. And the representation is a representation of the stabilizer of the conjugacy class. And these correspond to the flux and charge quantum number, respectively, of my sort of general or composite point-like excitation. Now we can go even further. We can handle this algebraic structure with the notion of co-multiplication and R matrix, and this will encode the statistics of the excitation. So its braiding and its fusion. So what's particularly nice with gauge models is that they can be defined in any dimension, quite straightforwardly. So for instance, in 3+1D, well, the relevant category theoretical structure is this bi-category of G-graded two vector spaces. But what matters right now is that the input data is a finite group again, and now a 4 cocycle instead of a 3 cocycle in 2+1D. And these Hamiltonian models in 3+1D, they yield not only point-like excitation like in 2+1D, but loop-like fluxes and point-like charge excitations. And now what we want to do is essentially to classify so the most general kind of loop-like excitation, and we are going to use the tube algebra approach again. Now the difference is that now, since the excitation has a topology of a circle, right, before it has a topology of a point, the energy which will have, the region for which the energy will be higher than the one of the ground state, will now have the topology of a solid torus, which is like a regular neighborhood of my loop. And this, my elementary loop-like excitation, will be classified by irreducible representations of the corresponding tube algebra, where the tube, right? So now it's not a cylinder exactly, it's more like a three-dimensional generalization of a cylinder, where I take a torus cross an interval. And below, I drew sort of the topological operation that underlies this tube algebra, which is I take two copies of this three-dimensional cylinder, I glue them, identifying the boundary conditions and so on. And then again, via some diffeomorphism, I can recover the original topology.
Excuse me, I have a question. In 2 dimensions, the boundary only have one choice, that is the circle S1.
Yeah.
In 3+1 dimension, the boundary have more choice. Here you choose to be torus. You can also choose to be sphere or D-2 Riemann surface. So what's why you choose torus, not other things?
So here, the torus is really because this is the regular neighborhood of a loop. You could indeed consider like so actually we know how to do the computation as well if you had a more general Riemann surface. And this we could imagine correspond to classifying more complicated excitation, like maybe a connected loops or something like this. But if we are only interested in the loop-like excitation, in that case, the torus is what we need. The sphere would be to classify point-like excitation, because the sphere is a regular neighborhood of a point, and you can do the computation with the sphere, and then you find that you're only classifying the charges, the charge excitations. If we want the most general composite of loop and loop-like fluxes and point-like charges, then we need the torus. And I will give more interpretation in a second about this tube algebra. Okay, so so we have the tube algebra, right? Then we sort of apply our general recipe in order to find the irreducible representation of this tube algebra. And now the question is, how do we actually interpret this irreducible representation? And the right interpretation is that these classify loop-like fluxes to which a point-like charge is attached in such a way that the quantum numbers associated to this flux and this charge are constrained by the presence of the threading flux. So we have sort of two fluxes and one charge. So the reason this is the case, if I go back to the previous slide, is because a flux, what it is, it's a violation of a stabilizer constraint with respect to the B operator, which penalizes non-flat connection. Now, a flat connection, right, we can only have a non-trivial holonomy if we have a non-contractible cycle. So if I want to sort of create a violation of my these stabilizer conditions, one way to do it is essentially to create non-constructible cycles. And this is by sort of the torus, right? The torus has two such non-contractible cycles, which is why we have two fluxes. And the charge correspond to, if you want, like a violation of the gauge invariance at the vertex at which these two contractible cycles intersect, non-contractible cycles. Now, what this implies, so the cartoon to understand what I just said is that you have these loops, right, where you think of it as a flux plus a charge, and then you have this threading flux that goes through the loop. And what we find is that as in 2+1D, we can endo this algebra with additional algebraic structure, namely a co-multiplication and an R matrix. And in that case, the processes they describe are the following. It describes a fusion of the loop-like excitations, but this fusion can only take place if they are threaded by the same flux, which is why this additional flux is fundamental. And similarly, the braiding encoded in this R matrix, in that case, the braiding means going through, so exchanging position by going through the other loop. This can only take place if they are threaded by the same flux as well. And so this is like a way to sort of mathematically encode this so-called three-loop braiding statistics that people have been considering for a while in the community. And we can go slightly further. We can show that the exchange statistics, so the one just well, depicted here, is governed by representation of the so-called necklace group, which is a motion group isomorphic to the braid group. And I mentioned that having representation of the braid group was like the definition of being an onion. So this is why, at the end of the day, we can say that these loop-like excitations, with respect to this braiding, behave like onions. Okay, so now, so this is the gauge models picture. What if we want to go further than that, consider a bit more complicated models? But at the same time, we would like to retain a lot of the nice features of gauge models. In that case, an obvious choice is to go to higher gauge models, where basically these are obtained by replacing the input group by so a categorification of the notion of group, which is a two group. And these models are found to have a higher gauge theory interpretation, which roughly, very roughly speaking, is the following. If a gauge theory is the theory of a one-form gauge field that encodes the parallel transport of a point-like object, a higher gauge theory is going to be a combination of both one-form and two-form gauge fields, and this can describe, encode the parallel transport of a string-like object instead of just one-like one. And generically, these Hamiltonians, they will have four terms. The first two terms, they are analogous to the gauge models because they are with respect to the one form. So we have the gauge invariance as before, which I will refer now to as the zero form gauge invariance to distinguish it from the other one. And the flatness condition, now I will call it the fake one flatness constraint. Fake because, as I'm going to explain, it's a bit twisted by the presence of the two form. And similarly, we have the analogous operators for the two form part, which is a one form gauge invariance. So this is a gauge invariance whose charges are one dimensional, and a two flatness constraint that now penalizes a non-flat two connection. So essentially, this flatness constraint tells us that if we have a contractible two cycle and we have a holonomy, like a two holonomy around this two cycle, it has to be trivial.
So,
okay,
and somehow this V means vertex and.
Oh yeah, sorry. So V is vertex, P is bracket, E is edge, and C is, well, here C will mean cube later, but
so
more
it's
generally.
A cube picture. It's a cube picture. So you have two directions like V vertex and bracket, and then on top of it, like E is edges between V and C is edges between P. You mean this as a cube picture?
Yes, yeah. C will, yeah. I use C because later it will exactly be a cube. More generally, it could be a three cell. So the input, so more explicitly, right? I said the input was a two group. So actually, we have two possibilities when we say two group. We have strict two groups or weak two groups, where strict and weak refer to this is the category theoretical formulation, not terminology. So a strict two group is can be succinctly defined as a monoidal category such that every object is invertible and every morphism is invertible. So this definition is nice and compact, but it's not very practical. So usually we use an equivalent description in terms of cross modules. And a cross module, it consists of four elements, two groups, both of which can be non-abelian, an action of G on H via by automorphisms, and a homomorphism from H to G. And these needs to satisfy some constraints referred to as the Pfeiffer identities. Now, weak two group, well, so it's a monoidal category such that every object is now weakly invertible and every morphism is invertible. And again, we don't use this definition in practice. We use the fact that these are characterized up to equivalencies by four elements again, a finite group, gamma 1, a finite abelian group, gamma 2, so that's one of the main distinctions, an action like before, and a cohomology class, so of gamma 1 valued in gamma 2. Now, today, since I want to focus on the specificity of dealing with a higher gauge model and try to remove some of the technicalities, first of all, I will not consider, I will consider a trivial topological action. So I will not pick a non-trivial cohomology class. And also, I would like, as mentioned before, I would like to work on the cubulation to make it visually nicer, let's say, which in that case, it forces me to work with a strict two group. If I wanted to deal with a weak two group because of the cohomology class, we would need to work on the triangulation, and it would make things a bit more obscure. So, so the model we get in that case, with input a strict two group, is the lattice Hamiltonian realization of the so-called Yeager homotopy 2 type TQFT. And this TQFT has two sort of limiting, so this model, they have two limiting cases. So the first one is the one we discussed before. So if I choose the second group to be trivial, then I'm reducing to a gauge model, which I already covered. And if I'm choosing the first group to be trivial, then I have a two-form gauge model, which you can show to be equivalent to a so-called Walker-Wang model for the corresponding premodular category. Okay, so the first thing we need in order to define a strict two-group model is to have a notion of strict two-group colored discretizations, or cubulation in my case. And to do so, it's relevant, very useful to go through the exercise to show the mapping exactly between cross-module and strict two groups. And more specifically, I will not reconstruct exactly the strict two group from the cross-module, but it's so-called delooping, which is a so-called one-object two-groupoid. So it's an example of two categories. So this one-object two-groupoid, well, so it has a single object, and which is represented by this black dot. The morphisms are labeled by group variables. And the two morphisms are labeled by H variables. And these are between morphisms labeled by G and a partial of H times G. Now, the composition rules are the following. So the composition of morphisms is dictated by the multiplication in the group. Okay? There are two ways of composing the two morphisms. Vertically first. In that case, it's dictated by the multiplication in H. And also horizontally, in which case is dictated by the multiplication in the semi-direct product of G and H. And so this is how you sort of reconstruct the delooping of a strict two group starting from a cross module, and you can also do the other way around in order to prove the equivalence. Now this, now using this, keeping this in mind, how do we define a strict two group coloring? Well, we need the notion of, well, a nice way to do it is via the notion of path two groupoid. So path two groupoid is another example of two groupoid, where the objects correspond to points on my surface, on a surface. The morphisms are a path between these points. And the two morphisms are so-called two paths between one path. So it's like a two cell, if you want, bounded by one path. And now, using this, I can concisely define a coloring of a discretization, a two-group coloring of discretization via two functors from the path two groupoid to the delooping of my strict two group. So more practically, okay, how does that work? So let's say I have a surface that I'm choosing to endow with a cubulation, together with a notion of branching structure. So it means having a numbering of my vertices from which I can induce essentially an orientation for the edges. And in that case, a given plaquette, it's colored as follows by a strict two group. So we have group elements on the edges, because the two functor, what it does is that it's going to map the edges of the two groupoid to the morphisms of my two group, which are labeled by edges. And similarly, we find that the plaquettes are then labeled by edge variables. And what's very crucial is that these two functor, it also preserves this condition here that my two morphisms, they can only be defined between this kind of one path. And this means that in this configuration, I must have a condition between my different group variables. And this is the so-called fake one-form flatness constraint I mentioned before. So why fake one-form flatness constraint? Well, the one-form flatness constraint would be the statement that it's a statement that holonomies along contractible cycle have to be the identity. On the lattice, it means that if I take a product of group variables around a plaquette, it has to be the identity. Now, since I have a two group, there is the two form part that is also involved. And now it's not quite a flatness constraint because I have this partial edge that sort of makes it fake. And this condition is very important because this condition ensures that this two group coloring is consistent. Otherwise, you would run into some inconsistencies. So given this, now let's look at the definition of the operators. So we have, first of all, the zero form gauge invariance, which is the usual gauge invariance. So it acts by right and left translations on the group variables, labeling the edges, meeting the vertex at which we act. So here, for instance, if I act on 0, I'm going to act by, it depends on the conventions you use, but here it means I'm going to act by left action on these two variables. And we see that there is also an action on the phase variable. And this action is here to make sure that the fake flatness constraint is always satisfied. We also have a one-form gauge invariance, which now acts on edges, and it's going to affect the plaquette variables of the plaquettes meeting at this edge. So it's going to shift the edge variable by lambda, but not quite lambda. We also have now we have a dependence on the group variables, the G group variables as well. And this again is to ensure the fake flatness is satisfied. Similarly here, we also have to act on this one for the same reason. So,
sorry, is it probably it's negotiable on which edge I would like to act, right?
Yeah, exactly. Yeah. Okay. If you act on 0, 2, depending on the conventions, it's yeah. And the last constraint is the so-called two flatness constraint, which penalizes non-flat two connection. So this, what it means essentially, it means that roughly speaking, the product of the edge group variables around a contractible two cycle have to be the identity. So now my cube is one such sort of, you can think of it as my contractible two cycle. So I want to enforce that the product of the edge variables around the cube is the identity. Now, this is not quite as straightforward because you have to remember that the edge variables, right, they are morphisms, right? They have a source and a target. And in order to do this multiplication, you need to make sure that source and targets match, right, to be able to compose them in the first place. Another way to put it is that these two morphisms, they have kind of a base point. They are based at one of the vertex around the plaquette on which they are defined. And to compose these two morphisms, we need to make sure they are all based at the same base point. It's like a frame of reference. They all need to be in the same frame of reference to be able so that we can compose them. And this, so this below at the bottom, and this is this composition of the two morphisms. We see that we have to act sometimes with G variables, and you can think of this action as a parallel transport. It's like I'm parallel transporting my two morphisms so that they are all at the same base point, and therefore I can actually compose them. Okay, so these are all the constraints. Now, so from this we can define the concept subspace. And as for gauge models and topological models in general, the topological invariance implies that given different cubulations, the concept subspaces will be isomorphic. What it means in practice is that we can do local unitary transformations that change the cubulation, but we remain in the same ground state sector. So practically, it means that, for instance, if I have two neighboring plaquettes and I'm considering a ground state on this, I can sort of merge the plaquettes. It's a local transformation in order to have an isomorphic state on a single plaquette, which is the merger of the two. So using all this, we can now consider the tube algebra in 2 + 1D as we did for the gauge model. Let me recall that the tube algebra with respect to the manifold, which is the torus cross an interval. So in order to define the ground state subspace explicitly on this manifold, I need to pick a cubulation. I should pick the simplest one possible because it doesn't matter which one I choose. So I should pick the simplest one. So in that case, it's just a cube. It's a cube such that the top and bottom faces are identified, and the front and back faces are also identified. And this gives me the topology of a torus cosine interval. Now I need to pick a flat 2 connection on this, which in that case depends on 6 covariables. The G variables are analogous to the ones for gauge models. And we have 3 others for the to form a part of the connection. And these are constrained by the fake flatness constraint on the boundary torus, because it's a plaquette at which the fake flatness must be enforced. And on the right-hand side, there is a more symbolic notation, which maybe is helpful, which also makes kind of explicit the fact that we can think of this element as a groupoid element. Okay, so this is just sort of a superposition of flat 2 connection. This is not yet a ground state on this manifold. The reason why is because we have to enforce the one-form gauge invariance along the single bulk edge. So this is something that doesn't happen in gauge models, because in gauge models, a flat connection is enough to write a ground state on the cylinder. Now that we have gauge invariance along edges as well, since there is a bulk edge in this manifold, we need to enforce it. So we apply the definition of the ground state projector at this edge. This is the formula below, which the details don't matter. But what it means is that it's actually labeled by an equivalence class of colorings in the bulk with respect to the one-form gauge invariance.
Clement?
Mm-hmm.
Maybe we should discuss how much time.
I'm almost done. Yeah.
Okay, sounds good.
So the cube algebra. So I'm not going to go through the details, but visually it looks like this, right? So here I'm forgetting about the group averaging as just mentioned to keep the notation simpler. But the first thing we need to do is to do the gluing, which means, as I mentioned before, it's an identification of the boundary coloring. So here it means I will have a delta function that sort of identifies the group variables on this plaquette here with the, well, along the plaquettes, at the plaquettes along which I do the gluing. Then I need to apply the ground state projector, and then I can do a diffeomorphism in order to recover a state in the original Hilbert space. So this is visually roughly how it looks. Then once we have the cube algebra, then we know how to compute the irreducible representation. Essentially, because all these tube algebras, we can rephrase them as groupoid algebras. And then we can apply the groupoid representation theory, which is like an extension of group theory, and systematically find the reducible representations. And this will classify like sort of the most general kind of loop-like excitation we can have in these models. And well, there are many components involved, and the interpretation is a bit tricky. But let me very quickly mention a few things. So the irreducible representations, they are labeled by 2 elements: an orbit, which corresponds to the magnetic quantum number, and a representation, which is the electric quantum number. Now, this magnetic quantum number, it accounts for 3 types of flux excitations. 2 one fluxes, which are the same ones we had for the gauge models, or similar ones, but also a two flux, which corresponds to the fact that the torus is a non-contractible 2 cycle, which means that I can have a 2 flux on this torus. So this magnetic number, it's like a mixture of these 3 fluxes, and the interplay between them is similar to the ones we had with the threading flux, this notion of a flux threading the loop and constraining the quantum number. Similarly, the electric quantum numbers, we have 3. One that is the 0 charge, so this is the same one or similar one as the one for gauge models. But now we also have 1 charges, so one-dimensional charges that correspond to violation of the one-form gauge invariance along the non-contractible cycles of the torus. And there is a non-trivial interplay between all this via the different constraints, but also the fact that we have to do this group averaging to define the ground states. And in order to really disentangle all these sort of components of these different excitations, it's useful to consider limiting cases. As I mentioned before, like, you know, we know what the one limiting case is the gauge model, so we know what happens there. The other limiting case is the 2-form model. The interpretation is also easy here. easy there, and then we can sort of combine all these to derive a consistent interpretation of these excitations. Okay, so let me conclude very quickly. So this was like an illustration of the tube algebra for a model that is a bit different from the, well, a bit more complicated than gauge models. It allows us to classify the excitations. As a byproduct of the construction, we can also get the ground state subspace on the three-torus. It can be neatly defined as the central subalgebra of the tube algebra. So that's also a nice way to get the ground states on the closed manifold. There are, well, a bunch of obvious follow-ups, which I won't even mention. Something I want to mention, which I think is quite interesting, is that as a byproduct of recent results regarding classification of 3+1D models, we know that there has to be a lot of duality relations between models in 3+1D. And in particular, we know that higher gauge models, certain higher gauge models, can be mapped to regular gauge models via a duality relation. And this is usually done at the level of the partition functions in terms of more like differential forms and so on. I think it would be interesting to understand this mechanism a bit more precisely or more, I don't know, more explicitly from a category theoretical point of view. And then from this, we could induce how to implement this duality on the lattice, and also what it means at the level of these excitations, possibly using some tube algebra techniques. Thank you very much for your attention.